So here are a few points about our equilibrium constant. Firstly, the units of Kc are going to depend upon the stoichiometry of the equation. Fairly obviously, if you think about it, because the stoichiometry does determine the powers that the concentrations are taken to. If the powers on the top and the bottom are the same, then there will be no units for Kc. If the position of the equilibrium is to the right hand side, in other words we have a high concentration of R and S and a low concentration of P and Q, then as Kc is equal to the concentration of products over reactants, Kc will be large. If on the other hand the position of the equilibrium is over to the left hand side, Kc will be small. Just as with the rate constant, the equilibrium constant is constant at constant temperature. So if you change the concentrations, you change the pressure, then you are not going to change the equilibrium constant. However, you alter the position of the equilibrium, the constant will remain the same. However, if you change the temperature, then Kc will change under those conditions. And just as Kc does not change if you change pressure or concentration of any of the reactants or drive the reaction over to one side, catalysts don't have an effect on the value of Kc. They speed up the rate of both the forward and the reverse reactions equally, so therefore the position of the equilibrium will not change and Kc will not change either. So let's have a look at an equilibrium. Carbon monoxide plus 2H2 going to CH3OH like that. Now, what is the Kc expression for this, and what are the units for Kc? Well, Kc is going to be equal to the concentration of the products over the concentration of the reactants, concentration of products, here CH3OH. Stoichiometry is a 1 to 2 to 1 ratio, so you can see that in this particular case that we've got to the power 1 divided by concentration of carbon monoxide multiplied by concentration of hydrogen squared, like that. So what about the units? Well, what we have here, our concentration is moles per cubic decimeter divided by moles per cubic decimeter for the carbon monoxide and moles per cubic decimeter squared for the hydrogen. Moles per cubic decimeter can cancel, which leaves us, of course, 1 over moles per cubic decimeter squared, which we can therefore convert to, well, the square of moles is moles squared, 1 moles to the minus 2 decimeters, decimeters squared is decimeters to the minus 6, 1 over decimeters to the 6. There we have our units for Kc in this case. Let's take another example, slightly more complex. Let's take 4NH3 plus 7O2 in equilibrium with 4NO plus 6H2O. Our Kc in this case is going to be concentration of NO to the power 4, concentration of H2O to the power 6, divided by concentration of ammonia to the power 4, concentration of oxygen to the power 7. That's our Kc expression. Our units look a little bit monstrous, but let's see how we get on. So we've got moles per cubic decimeter to the power 4 and moles per cubic decimeter to the power 6 divided by moles per cubic decimeter to the power 4 moles per cubic decimeter to the power 7. So if we look at that, we can get rid of moles per cubic decimeter to the power 4 and moles per cubic decimeter to the power 4, and we can take moles per cubic decimeter to the power 6 and get rid of 6 of those, and that leaves us therefore with 1 over moles per cubic decimeter, which we can convert of course to mole to the minus 1 decimeters to the plus 6 plus 3. Notice always when you've got these, you're going to have a 1 to minus 3 ratio of moles to cubic decimeters. Have this problem where we're looking at the contact process, the production of sulfuric acid. This is one of the processes involved in that. So we've got sulfur dioxide reacting with oxygen to give sulfur trioxide. Now note the stoichiometry of this equation. We've got 1 mole of SO2 reacting with half a mole of O2 to give 1 mole of SO3. I could have as easily written it as 2 moles of SO2 going to O2 and to give 2 moles of SO3. Now in that particular case the Kc expression would be different, and the units of Kc would also be different. Let's have a look at Kc then to start off with. So Kc is going to be equal to concentration of SO3 divided by concentration of SO2 and concentration of O2, but the concentration of O2 is to the power 1/2, like that. So that is our Kc expression. Now if we look at the units for this, moles per cubic decimeter for the concentration of sulfur trioxide, moles per cubic decimeter for sulfur dioxide, and moles per cubic decimeter to the power 1/2 for the oxygen. Moles per cubic decimeter and moles per cubic decimeter cancel, and that therefore leaves us with 1 over moles per cubic decimeter to the power 1/2. Multiply that out, we get 1 over moles to the 1/2 decimeters to the minus 3 over 2, and therefore if we take that up to the top, that will give us moles to the minus 1/2 decimeters to the plus 3 over 2. Odd units, but that's the way it comes out if we have that particular equation. Now, second part of this question is what happens to Kc if the temperature is increased? Well, let's just consider that, shall we? So here we have our equation, and if we increase the temperature, Le Chatelier's principle will apply. The system will oppose that increase in temperature, and it will favour therefore the endothermic process. The exothermic process is to the right, the endothermic process is to the left. So the position of equilibrium will move over to the left hand side in this particular case. So the concentration of SO3 will decrease and the concentrations of SO2 and O2 will increase. Therefore Kc will also decrease. It will get smaller